In this video, we're going to see a few examples of Smith charts to get some practice with them. We're going to start with some familiar resistive terminations. We're going to assume Z0 is purely resistive 50 ohms in all of these examples. The table on this page summarizes some common terminations, and I've drawn point 1 on the Smith chart on the left already. When we terminate a 50 ohm line in 50 ohms, we expect there to be no reflections. That means both the real and complex parts of gamma are 0, so our point is at the origin of the gamma plane. It also means that Rn is equal to 1 and Xn is equal to 0. As a reminder, we found Rn and Xn by dividing the real and imaginary parts of ZL by 50 ohms. We can see that point 1 is on the Rn equals 1 circle, and the Xn equals 0 circle, which is just the x-axis of the gamma plane. So this point matches our expectations both for its location on gamma and its location on our new overlaid Smith chart axes. If we double the load resistance, gamma becomes 1/3 plus 0j, and the normalized impedance becomes 2 plus 0j. Take a second to think about where you'd put that point on this plot. This is the right spot. We can certainly see that it's on the Rn equals 2 circle, and the Xn equals 0j circle. It's harder to tell that it's at gamma equals 1/3 plus 0j, but it's plausible. We'd be able to judge exactly what gamma value it was more easily if we knew the radius of this outermost circle that we keep drawing. This guy. As a way to figure that out, we could imagine drawing point 3, which changes RL to an open circuit. That results in gamma equals 1, Rn equals infinity, and Xn still being 0j. Think about where you'd put point 3. There's no Rn equals infinity circle drawn on here, but we can see that Rn circles get smaller as we increase Rn, and you may recall that the radius of them was 1 over 1 plus Rn. And we know that all the constant resistance circles intersect at the point 1, 0. So point 3 winds up all the way on the right side of this circle, which we've now identified as having a radius of 1. To say that another way, the outer circle is the unit circle on the gamma plane. Point 4 represents a short load, so gamma is minus 1 and Rn is 0. Where do you think that point will be? That point winds up all the way on the left side of this circle. Points 3 and 4 make point 2 look pretty reasonable. It's about 1/3 of the way to the outer circle. Real load impedances result in real gamma values, and we see that all of these points fell on the real axis of the gamma plane, so far so good. The Smith chart becomes really useful when we start making tricky loads like this one. Here we have an inductor in series with a 50 ohm resistor. Because the impedance of an inductor is j omega L, we're going to see this load trace out a locus of points on the complex plane as we vary omega. For very low omega, we know the inductor looks like a short, so we'd expect the locus to start at 0, 0 on the complex plane in honor of RL matching Z0. For high omega, the inductor looks like an open, so we'd expect the locus to finish up at 1, 0 on the complex plane. In between, we'd move around the constant reactance circle of Rn equals 1, as our value of Xn becomes more and more positive. We see exactly that on the Smith chart. This locus includes 0, 0 and climbs across different Xn values along the Rn equal 1 circle. Series inductors move around the positive half plane like this because j omega L is a positive reactance. Series capacitors would move around the negative half plane because 1 over j omega C is equal to minus j over omega C, which you can see by multiplying the top and bottom by j. And that's a negative reactance. Another tricky termination would be a shunt capacitor. At low frequencies it would be open, so we'd expect a reflection coefficient of 0 at the middle of the Smith chart. At high frequencies it will be a short circuit, so it would show up at the gamma equals minus 1 point on the left of the Smith chart. Describing what happens in between demands that we use the admittance and susceptance lines instead of the resistance and reactance lines. Our load conductance GL is 1/50th of a Siemens, and our characteristic conductance is also 1/50th of a Siemens. So the normalized conductance is 1. Our normalized susceptance is j omega c over 1/50th, so we'll sweep out a path on the complex plane as omega is changed. One oddity of the admittance axes is that positive JBN on the y-plane maps to circles on the negative imaginary gamma half-plane. So this curve moves across positive JBN coordinates, which are on the bottom of the Smith chart. That's a little weird to remember, but there's a convenient mnemonic. The bottom half of the Smith chart is for capacitors, either in shunt or series, and the top half is for inductors, which are either in shunt or series. Finally, if we look at our delayed load, we can see the locus of points it occupies as frequency changes is described by a circle that's concentric with the unit circle. This is just our generalized gamma g being swept around the plane as the phase it sees increases. We picked this representation because it would be easy to draw gamma g as a phasor, and we're just seeing that here. So in summary, the Smith chart lets us translate easily between loads and reflection coefficients. Inductors and capacitors trace out loci of different reflection coefficients as frequency is varied, and C is always on the bottom half plane, and L is always on the top. And the admittance axes are kind of upside down. They map positive JBN to negative J times imaginary gamma.